This conference will now be recorded.
All right, Math 211 students, this is section 3.9, the antiderivatives. I just wanted to go through and do a few of the examples that we skipped over, starting with example 3, part A. We did part B because, we did part B because it was a little bit harder, so we're going to go through part A now. Because this one had you start with a second derivative and work all the way back to the original function. So this one is starting you off with f prime and you're just trying to find the original function. So we're going to be using antiderivatives here. So the first thing I would probably do is write that as x to the 1/2, and we should maybe just distribute that through. So this is 6x to the 1/2 and plus 5x to the 3/2. So the antiderivative would be the function f of x, and remember we raise this to 1 power and divide by the new power, so this is going to be 6x to the 3/2 times the reciprocal, so that'd be 2/3, plus 5x to the 5/2 times 2/5, and then plus our c, because remember that's our constant of the integration. So let's see if we can reduce this. So this would be 6 divided by 3 is 2, so this is going to be 4x to the 3/2. The 5's cancel here, so it's going to be 2x to the 5/2, and then plus c. So remember, this is the most general antiderivative. This is the family of all the antiderivatives, but we were given an actual function value, so we should be able to figure out what c is. So remember, you're plugging in 1 for all your x's. So this is to the 3/2 plus 2 times 1 to the 5/2 plus c. But we know that f of 1 is 10, so we can replace that with the number 10. This is 4 times 1 again, because it's going to be square root, but then it cubes, and it's still going to be 1, plus 2 times 1 plus c. So we have 10 equals 4 plus 2 plus c, that's 6. If we subtract that over, that's going to be 4 equals c. So my actual formula for my function here, this is the particular solution for this original f prime that goes through this point, is f of x equals 4x to the 3/2 plus 2x to the 5/2 plus 4. So there's that function value. Something similar for example 4, we skipped over this one because it was a similar situation. This is the particle is moving according to a given data, and find the position of the particle. Remember, position function is s of t. So this is starting us with acceleration, so we need to move all the way back from velocity, and then we need to move to the position function. So if we take the antiderivative of a of t, that's going to be v of t, because velocity is the derivative before acceleration, and that will be raise this power, so that's going to be 2t squared divided by 2 plus 1 times t now, and then plus c. So this would be v of t is t squared plus t plus c. So we know that velocity at 0 is -2, so v of 0 equals 0 squared plus 0 plus c. So then that's -2 according to this statement up here. These are both zeros, so that's just going to be 0 plus c, so c is -2. So that means my velocity function is t squared plus t minus 2. So then for my next one, I'm going to do a different color. I'm going to take this function and take its antiderivative, and that will be the position function, s of t. So that's going to be t to the 3rd over 3 plus t to the 2nd over 2 minus 2t plus, I'm going to use d this time instead of c, just to differentiate. And then this is s of 0 equals 3, so s of 0 equals 0 cubed over 3 plus 0 squared over 2 minus 2 times 0 plus d. S of 0, though, is 3, so this is 3 plus equals 0 plus 0 minus 0 plus d. So d is positive 3. So my final answer for my position function is s of t equals 1/3 t cubed, that's just another way of writing this, plus 1/2 t squared minus 2t plus 3. So there is the position function for that particle. And then the very last one that we didn't get to do in class together, it was the stone was dropped off a cliff problem. So let me see what we've got about this one. It says, a stone was dropped off a cliff and hit the ground with a speed of 120 feet per second. So that is a velocity. What is the height of the cliff? Use 32 feet per second squared for acceleration due to gravity. So we know that acceleration is negative 32 feet per second squared. Initial velocity, because we don't know specific, we know this is when it hits the ground, but we don't know how long that was yet. So initial velocity was 0, because you always start out with 0 velocity. Your initial position, we don't know, so we're going to call that h. So let's go through and figure out some of our pieces of information. So if a of t is just our acceleration, then we know that that is also, a of t is v prime of t. It's its derivative. And so then if we take an antiderivative of this, that means that v of t would be the antiderivative of a, which would be a times t plus a constant c. And velocity at time 0 is, because remember, you're dropping it off a cliff. You don't have initial velocity if you just walk up to a cliff and you just let something go. It starts having velocity, but not at moment 0. So v of 0 is going to be our 0 times a plus c, which is just c. So then we can write v of t like this. We can say that it is a times t plus initial velocity, because c and initial velocity are exactly the same thing. So then if we take the antiderivative of v of t, then that's going to be s of t, and this would be a times t squared over 2 plus v sub 0 times t plus c again, or d if we want to use a different variable. So that means that s of t is 1/2 a t squared plus v sub 0 t plus d. And we know that our initial height, that's what we're solving for. So we're just going to call this guy s sub 0 is initial height. So if we let that be d, essentially, yeah, because s of 0 for the position function, let's prove it, equals s of 0, which is 1/2 a times 0 squared plus v sub 0 times 0 plus d. So that means that we can rewrite this position function as s of t equals 1/2 a t squared plus v sub 0 t plus s sub 0. So this is a standard what we call a projectile motion function. And notice now we can put an acceleration here, and we can put in our velocity that we know, and then we can use that to help us find this height. So s of t is going to be 1/2 of negative 32. So that's going to be negative 16t squared, because remember we're letting that be negative 32. This is initial velocity, which we know is 0 since you just dropped it off the cliff, so that's going to go away. So that's just plus the s of 0. Now, if you take a derivative of that, then that means that the velocity function would just be negative 32t. And we do know our we know our velocity at the time it hit ground. So this is kind of what we're going to do. The first time I'm going to use this is I'm going to use v of hit ground, because we don't know when that happened. We need to know. That's kind of how we're going to figure out what was the height of the original cliff. So we have to use this velocity, and notice this is hitting the ground. It's heading in a negative direction. So when we plug this in just a second for v of t, because that's what this is, v of hit ground time, then we're going to have that negative 120 is negative 32t. We divide by negative 32, and it looks like our cliff drop took us 3.75 seconds. I worked that out on my calculator earlier. So this is when it hit the ground. Now that's not what they asked for. They asked us for the height of the cliff, but that'll help us find the height of the cliff, because we can solve now when this happened. So when s of 3.75 happens, that's when we actually equal 0, because that is when we hit the ground. So if we set the whole function with 3.75 in for our t's, so this is right here, we'll be able to find the initial height of that cliff. So this is negative 16 times 3.75 squared plus the s sub 0, which I'm trying to solve for. And we know this is equal to 0 since it's when we hit the ground. Now, when I worked this out earlier, I didn't write out my answer. So let me see what that is as a decimal. So 3.75 squared. And then that's times a negative 16, which I know it's going to be negative. So that's negative 225. Negative 225 plus s sub 0. And then we just add that over. So it looks like our initial height of our cliff before the rock was dropped was 225 feet in the air. So we used the idea of they gave us acceleration and we kind of knew that velocity was just 0 because they let go of the rock. They didn't throw the rock with any force. And we used the idea of antiderivatives to go from what was acceleration, what would be the antiderivative of that, plug in some things we know, find the antiderivative again to find position function, plug in things we know to find the d, and then we had our equation. So once we had our equation for position, we could take the derivative to get the velocity function. Then we knew the velocity at the time we hit the ground, so we plugged that in, and that helped us solve for what time did we hit the ground. And then using that back in the position function, we were able to solve for the initial height. So there's a lot of back and forth in this problem, but it's a good one to see the connections between the antiderivatives. And that is it for this video.